window or video open is allowing to appear in YouTube, okay? So I will say that in Spanish in some way, okay?
No problem.
Okay. Okay. ¿Qué tal? Muy buenas tardes tengan todos. Hoy tenemos un coloquio. Les quiero avisar a toda la gente que está conectada que todos aquellos que tengan su cámara activada deben aceptar que se muestre su imagen por YouTube. Entonces, aquellos que no deseen aceptar que su imagen se transmita por YouTube, les pediría que apaguen su cámara, por favor. Bueno, muchas gracias. Bueno, pues hoy es un placer para mí presentar a la profesora Petra Rudolph. Okay, it's a great pleasure for me to introduce Petra Rudolph. And let me just to mention a few things about her. She was born in Munich, in Germany. She studied physics at the La Sapienza, la Università di Roma, La Sapienza, when she specialized in solid-state physics. Then, in 1987, she joined the National Social Science Laboratory in Trieste, and for the following 5 years. Okay, I don't understand very well here, but she was also at Bell Labs in the United States in 2 different periods where she started to work on the newly discovered fullerenes in that moment. Okay, she got the PhD in 1995, and then she moved from postdoctoral research to lecturer and senior lecturer before taking up the chair in experimental solid-state physics at the University of Groningen in 2003. She is there in the University of Groningen. Her principal research interests lie in the areas of condensed matter physics and surface science, particularly molecular motors, 2D solids, organic thin films, and inorganic organic hybrids. She was published about more than 260 peer-reviewed articles, 32 book chapters. She has guided 34 master science students and 27 PhD students who successfully defends their thesis. And she has supervised about 23 postdoctoral research fellows. Petra Rudolph was the president of the European Physical Society until 1 month ago, more or less, no? And yes. For the last 2 years, right? And of the Belgian Physical Society also in 2001. She was elected member of the German Academy of Science and Engineering and foreign corresponding member of the Academy of Science of the Institute of Bologna, also honorary member of the Italian Physical Society, fellow of the Institute of Physics of the Dutch. It's quite difficult. I don't speak any. Okay, of the Dutch Physical Society, and fellow of the American Physical Society. Okay, so she's really very well recognized in the physics community. For her work on molecular motors, she received in 2007 the Descartes Prize of the European Commission also. And in 2013, she was appointed officer of the Order of the Orange Nassau by the Queen, the Beatrix of the Netherlands, when she's now in the Groningen University. So for me, it's really a pleasure having here Petra. We know each other since some years ago, and she's really a wonderful scientist, but also a very wonderful person. And thank you so much for being here. And I'm sure that people will be very interested in your talk. Welcome, Petra. And we want to know more about the 2D playing Lego with 2D materials.
Thank you very much, Cecilia. It's a great pleasure to be here. And as I said before, the Corona crisis is not only bad, it has also very nice sides. And this is one of the nice sides that we are together today. So thank you very much for your kind introduction. And I will share my screen. Yes, I suppose that you can see it now, right? Yes. Okay, so I will tell you a little bit about what we do with two-dimensional crystals. I will first talk about single layers, and then I will talk about pillar structures. And most of the work that all the work that I'm talking about was done in Groningen. So the institute is the Zernike Institute for Advanced Materials. And of course, 2D materials started in 2004 with this famous paper by with first authors Novoselov and Heim, and with graphene came also the Nobel Prize for 2D materials. And people now always say that they got the Nobel Prize for making graphene. That is not true. They got the Nobel Prize for groundbreaking experiments regarding the two-dimensional material. So we all know what graphene is. Actually, it was theoretically predicted in 1947, and very many surface scientists like me have worked with graphene long before it was called this way. It was called before graphitic carbon, and we regarded it more as a nuisance than as something that we like to work with. But then with the interesting papers that appeared, everybody realized that it has a lot of exciting properties. So up to now, there are very few commercial applications yet, but they are going to come because we all know that it's really exciting from many aspects. The fact that it is such a stable material, that it is inert, but it is conducting electricity so fantastically, that it is conducting heat so fantastically, and that it is impermeable. All these things give it fantastic properties, and many applications are foreseen as capacitors, gas sensor for batteries, hydrogen storage, but also, of course, electronics and spintronics. And graphene does not look like that. When you see it in reality, it looks more like you see here. So very often it is not completely flat, but it is sort of crumpled. And that's how it looks like on surfaces. You probably all know that there are very different ways to make graphene. Scotch tape was the method used by Jaime Novoselov and also by many of the people who investigated the exciting transport properties, but that is of course not a method that you can scale up. So people found other ways to make it, for example, from silicon carbide. Now silicon carbide is very expensive, so you have to have a good reason for using it, but you can get very nice graphene on top of that. Most people work with chemical vapor, deposition and transfer, or with chemical exfoliation. And I shall show you some results of both methods. So this is something that we did quite a few years ago. We showed that you can prepare graphene by chemical vapor deposition both on metallic surfaces, as most people do, and on insulating surfaces. And you see that the quality is this my echo? No, is it okay? The quality of the material is quite good. It has very little defects. And you can see that on the oxidized surface, you see a sort of a moray structure which comes from the oxide, which is below. And it actually turns out that on the copper oxide, you get a very good quality of graphene, because there are the copper atoms on the surface that actually act equally as catalytic centers as the copper alone does. But when the methane breaks up into OH and CH3, you have a different diffusion on the oxide, and that is actually a positive thing to happen. What is even more exciting is the fact that when you, well, now it's a bit difficult because you have one part, the exciting result is under my picture, so you actually don't see it. That was a bit stupid that I didn't think of it. Well, actually, this is the valence band, the photo emission of graphene on the pure copper. And you see that you see the Dirac cone here. You only see part of it, but it is below the Fermi level. So with photo emission, you can only see states which are occupied. And you see that the point where the two curves cross is below the Fermi level. So on pure copper, there's actually a transfer of charge from the copper to the graphene. Instead, if you could see what is below our photos, namely the dispersion on the copper oxide, you would see that now this point moves up, and it's actually behaving like freestanding graphene in this case. So what is also very nice is that the Fermi velocity on the graphene grown on copper oxide is in perfect agreement with the theoretically predicted value of freestanding graphene, while on the metal it is 3 times smaller, so on the metallic surface. So actually we can grow graphene on the oxide in a way that we have graphene that behaves like freestanding graphene, so that we have no influence from the substrate, and that's very nice. So, of course, if you want to grow it on for a large production, you don't do that on a copper single crystal, as I have shown you. But what people do nowadays is mainly grow on liquid copper. And when you do that, as you can see here in this example, you get islands which are perfectly oriented and merge, and you get a very beautiful quality because the domains align and they merge, so you get quasi single crystal graphene of very large dimensions. So then you can ask, well, for electronic applications, you actually need a gap. So how can you get a gap? From semiconductors, we know that doping can be used, and also here doping can be used even if it is a semi-metal, because the density of states at the Fermi level is very small. So what one can do is to dope it with boron and nitrogen, and then a gap actually opens. But the problem is that you actually phase separate. So the boron and the nitrogen, they don't like to mix with the graphene, but you get islands of boron and nitrogen in the middle of the graphene. And that Angel Rubio published a very nice comment in Nature Materials, where he explains that even this situation can be useful if the domains are small enough. We are working on this. So right now we are producing domains which are of the order of a few nanometers, which is still too big. and we still hope, so we are working now, we are trying to make it that we get single hexagons of boron and nitrogen, and we hope to reach that soon. We are not there yet, but this is a big challenge where lots of people are working on. You can also play these games with other 2D solids. A material that we have worked with quite a bit is germanane. So what does germanane look like? If you look from above, it is also a hexagonal structure, but actually every germanane atom is terminated by hydrogen. It was first synthesized in 2013. One starts out with a germanium calcium compound, and then with acid, one gets the germanane. What we did with it is I collaborated with Dimitris Kournis from the University of Ioannina to find a faster synthesis procedure. Well, they found it, but then they characterized it together with my group, and we just published that in Angewandte. So while this method that was published in 2013, it takes about a week to get germanane, here it takes minutes. And then, of course, we use this material to try out several properties. So, for example, what we made together with my colleague Bart van Wees, who is just above me, he made this device with it to measure how it behaves. And what he found is that the resistance varies with channel length, and that there is a peak close to zero. So also this is a material which has very little intrinsic doping and which behaves quite well in conductance. So it's an ambipolar device like graphene, but of course we are still at the beginning for what the quality of the material is concerned, because the mobilities are far, far lower than the theoretically predicted mobilities. But that was the same with graphene in the beginning. So we have hope that this will improve in time. What is extremely interesting is that if you now heat this material in a device configuration, and that was done with my other colleague Justin Ye, who is also at the Zernike Institute. So he made another type of device structure also with our material, and then he started heating. And what you find is that you lose hydrogen and you get a new form of germanium containing, it only contains germanium, but germanium can have many different many different structures. So we think it is germanine what we get, because the Raman indicates it. The conductivity is certainly a metallic conductivity, etc. And it is not germanium, because the conductivities of germanium, you now don't see the values because our pictures are below it. But the annealed germanane has a much better conductivity than any of these other compounds. And that's something that is certainly worthwhile pursuing now that there are these interesting new articles about the fact that there are different metals, and germanium is one of those that forms these different metals. So it's very exciting field where we will certainly continue to work. How do we put germanane on a surface? Well, we use actually a very old technique that was invented by Erwin Langmuir and Catherine Blodgett, what they did was to put amphiphilic molecules on the water surface, so they will not drown in the water, but they will stay there. And then you can compress it, and then you can come with the substrate and you can pick up your layer. And if you pick it up in this way, it is called the Langmuir-Scheffer method, actually, and Scheffer was a technician in their lab. So you can do the same thing with graphene or with germane. So with germane, it's particularly simple. You just disperse germane in ethanol, you deposit it at the surface, it floats, you come with, you can compress it to get the packing of the layers, then you come with your hydrophobic substrate and you pick it up and you get a close packed layer. As I can show you, this is a stable layer. So depending on how much material you put on the surface, you get the transition from a 2D gas to a 2D solid or liquid at different pressures. So you get a stable layer. At the surface, you don't need any surfactant. And here you see, I don't know if you can see the contrast is not very good, but you have the little flakes which touch each other. And if you measure the distance, you see that the flake is 1 nanometer in height, which is what you would expect if there is some water on top. So that is what you expect to get. Now, what we tested with this was also completely different properties, namely antibacterial properties. And what we used for this study were both gram-negative and gram-positive bacteria. And of course, I'm a physicist, so this was not done in my lab, but we collaborated with people who know how to do this, in particular, the Stamatis group at the University in Ioannina. And what they found is that overnight exposure inhibits bacteria growth for more than 80% in the first 6 hours for both gram-positive and gram-negative strains. And that is a very positive thing because the germane is not not something which is particularly difficult to prepare. And one can also make the monolayers and see that depending on the concentration in solution, one can also kill both types of bacteria very efficiently. So it's not only good for optoelectronics, as people might think, but there are also other exciting properties, and we are just at the beginning of discovering it. Now I want you to think of something completely different, namely of superconductivity. So you know that superconductivity has been found in several very thin materials. So the first was metallic monolayers, lead, and then there was alkali decorated graphene. And if you look at it, this is what it looks like. The critical temperature is very low, but there is no doubt that it becomes superconducting. So this material, you can also use something different. Instead of using carbon and alkalis or carbon and lithium, you can use magnesium, and you can use boron, and you get magnesium hexaborite. And you can think that this is superconducting in the bulk. In fact, it has a transition temperature at 39 Kelvin. And you can ask yourself what happens This is also a layered material, so you can make it very thin, you can make it only a few layers thick. Is it still superconducting? Well, that is something that we studied with angle resolved fault emission. So here we are looking at the density of states around the Fermi level. And what we did was always to measure a real metal which does not go superconducting, namely tantalum, with it. And so when you have just one layer of magnesium hexaborite and you measure it together with the tantalum, you see that in both cases, all the line goes through the Fermi level. So this doesn't have a gap. We are growing it on magnesium. So the first layer is just a normal metal at low temperatures. But when you go to 4 layers, there is no change, still a normal metal. But when you go to 6 layers, you see now the lines don't cross at the Fermi level anymore. And when you go to 8 layers, it goes even further away. So we have a gap opening here. Below 6 layers, we don't have a gap, and above 6 layers, we do. And we can also follow how this changes with temperature. And then we did these measurements because there had been these predictions. So the prediction had been that the temperature should go, the critical temperature should go like this. And that was not at all what we were seeing. So we were very surprised, and these oscillations were supposed to come from the quantum effects, etc. And we didn't see anything like that. So we went to the University of Antwerp because our friends here, and in particular Jonas Berkert in the group of Francois Peters, he agreed to help us and to calculate. And what he did do is to consider the monolayer first. And what he found is actually that the story is completely different. So the predictions that have been made before never really considered surface electrons. Or when you have a very thin layer, of course, the surface electrons are the most important. So what he found is that actually, while in normal bulk magnesium diborite, you have 2 types of Cooper pairs with different different gaps. When you have only 1 layer, or when you have surface atoms in a very thin layer, the surface electrons, you actually get 3 types of Cooper pairs. And they are all coupled, and one can get a very different behavior than if one doesn't consider it. So what he did is to look at the 3 different electronic states and to calculate this 3-component conductivity, and to look how it varies. So you have the surface state and you have the sigma and the pi electrons. And he looked how it varies with thickness. And we were very, very happy to see that his predictions go very well with what we found experimentally. And that is actually something which is also very exciting in perspective, because it tells you that when you make very thin layers, really surprising things happen. And that is now taken further by looking at how one can combine these layers and have coupling between neighboring layers to induce exciting properties. That was first proposed by André Geim and and his wife in 2013. So Irina Grigorieva and has worked a lot on the optical properties since then. Other people have looked at other properties of these layers. And what is very exciting is that you get, when you overlay lay these layers, you get the moire patterns because you get a different strain between the layers also. And what one can see is that the interaction with the different atoms below is very different depending on the atom. So for example, if you put a layer of boron nitride and you put graphene on top, there is a different interaction between the boron and the graphene and the nitrogen and the graphene. And these things are studied a lot theoretically, but the first results are coming up. And we are also working on this right now. So the band structure can really be engineered in these cases by the relative alignment of the two layers. One can have surface reconstruction, one can have charge transfer, one can have proximity effects. And it's particularly interesting when you do this with transition metal dichalcogenides. One can have many body instabilities, charge density waves, spin density waves, superconductivity. And these twisted bilayers have very exciting properties. So the twisted bilayer of graphene is superconducting at a certain angle, but other of these materials become ferroelectric when you make these very thin layers, and you also can get topological phases. So this is a very exciting field. I have 2 PhD students who are working on it. But they don't have enough results yet to show you something. What I would like to show you now is what happens when you go into 3 dimensions. So when you really play Lego in this way. We were very intrigued already in 2008 by this, because George Frudakis came out with this structure, which is graphene connected by carbon nanotubes, where he said that this would be a fantastic material for hydrogen storage. And of course, I have no clue how one can make a material like that, but we immediately said, well, we can make something like this. So graphene and fullerenes in between. And this I do with people who have a lot of experience in pillaring, and that is the group of Dimitris Kournis at the University of Ioannina. So of course, being Greek, they are very familiar with pillars, also on the nano level. So we had the first common PhD student then in 2013. And what Kostas did was the following. He started out with very tiny graphite flakes, so just a few layers of graphene. And then in order to do something like this, I mean, you remember fullerenes are quite big. It's more than 0.5 nanometer across a fullerene molecule. So it does not go in easily. You have to first get the layers apart. And the way you do that is by intercalating nitric acid. And then you expose it to the fullerene, and the fullerene at this point goes in. And the nice thing is that you just have to heat a little bit and the nitric acid goes back out, and you have exactly this structure as we could show. It's not particularly good at hydrogen storage, but it was a very nice adventure to start to work on pillared structures. And since then, we have done a lot of pillared structures together, but we work very often with graphene oxide, because the nice thing with graphene oxide is that when you bring in a molecule, this molecule can then bind to the functional groups on the graphene oxide, where you have OH groups, you have all kinds of functional groups on the sheets. And the NH2 of this molecule here binds, And in this way, you get a permanent pillar in here. And the nice thing of these structures is that you create a material which is porous, but the pores have a very well-defined size, because the size is given by the distance between the planes, which is determined by the pillars that you put in. But by putting the right kind of molecule, you also create a pore with a certain chemical affinity. And we have been doing that for quite a few years by now, and I'm going to show you some examples of it. What can you use these pillared graphene or graphene oxide for? Well, for anything that you would like to put in a pore. So you can use it to separate gases, you can use it to put little catalyst particles in there that won't get bigger than a certain size because of the size of the pore. And you can selectively get gases in, because if they are too big, they don't get in. You can put medicine in and release it under certain conditions. You can do drug delivery. You can also catch things from the environment in these pores, environmental remediation and gas storage. I'm going to show you a few of these applications which we tried out. So again, one thing is to put something in the adamantylamine that I just showed you is actually a very toxic molecule. So Haristamatis at the University of Johanna had the idea that we could use it as a poison for cancer cells. And it actually works. So here you see graphene oxide alone, adamantylamine alone, and the combined material, the pillared material. And what you see here is that graphene oxide itself leaves normal cells quite undisturbed. A little bit it does, but very little. And also the pillared structure is not very negative on the healthy cells. But while the adamantylamine is very very toxic to healthy cells and to the cancer cells that we use. But what you see here is that the pillared structure actually is very toxic to the cancer cells, but not to the normal cells. And that's something which is very nice because actually it's something that is needed when operations are done on cancer, especially inside the bowel or places like that. One would like to put something which kills any cells that have been overlooked. So all this has now been passed on to our colleagues in the biomedical sciences, and they continue to look how to continue and develop this into a medication. You will ask, well, why are the cancer cells killed and the normal cells are not? Well, we don't have a definite proof yet, but what we think happens is that because the acidity in a cancer environment is different from that of a normal cell, that our adamantylamine goes out, leaches out, and poisons the cells, while in the normal ones, it remains protected between the graphene oxide layers. So another thing is aromatic pollutants that are in the water. They are produced by the pharmaceutical industry, by the petroleum industry, by dyes, by pesticides. And these pollutants end up in the soil, in the groundwater, and in the drinking water. And so one needs to filter them out. And these pillared structures are quite good at it. So I'm showing you here various chlorophenol absorbed from the water. So the way that you know whether it's absorbed is to compare the UV spectra of solutions with a known phenol concentration with the ones that we get if we add our pillar material, and from that we can determine how much is absorbed. If the molecule is small enough to go in the pores, it's absorbed. If it's too big, it's not absorbed. So again, you can tailor your material to absorb what you want it to absorb. And you can see exactly that if you compare the space that is occupied by the pillar with the molecules, you see that the first one goes in easily and is very nicely trapped. This one, which is a bit bigger, is already very difficult, and the other one not at all. So one can trap the molecules if one adapts the size of the pore to the size of what you want to trap. Of course, this is also useful for herbicide remediation, but here we do a different trick. So this herbicide here, chloridazone, has been used enormously in many parts of Europe because it was used in agriculture, because people thought that it was harmless or relatively harmless. But the problem is that it doesn't degrade. It just breaks up, and this is still aromatic pollutants, and they stay on for years and years. And in many parts of Europe, the concentrations are now reaching levels where one cannot neglect it anymore. So actually, what you can do now is to use it as a pillaring agent. So you expose the graphene oxide to the polluted water to the graphene oxide, and it is these molecules which will go in and which will attach to the graphene oxide. And actually, without any optimization, the sorption properties are already at the same level as activated carbon, which is what is currently used. And it is much cheaper than activated carbon, and the preparation is more environmentally friendly. So that is something that one will certainly work on also in the future, because if one tailors the functional groups a little bit, I'm sure that one can get even better absorption properties. I told you drug delivery. Now, one drug that all of you know is ibuprofen. It is very bad for your stomach, but if you get it in your intestine, where it is then absorbed in the other part, to go to the other parts in your body, it is a very good painkiller. So what one would like to do is to give it to you in a way that it passes your stomach without interacting, and only gets out in the intestine. And graphene oxide seems to do the trick also here. So this is the release when you use it inside graphene oxide. In the gastric liquid, it is not released, or released only very, very little. And instead, in the intestine, it is released very well. So this is another thing that we have passed on to our colleagues in pharmacy who are working on it to see whether one can develop this further. CO2 storage, you know the problem, billions of metric tons emitted in the air annually. Can these pillar structures help? Well, what we use as a pillar here is little silicon oxide cubes. Actually, they also have these ligands on them, and we put them again between the graphene oxide layers. That's something that we have just published now, and we look how it does for CO2 storage. And we actually dry it by freeze drying and by air drying, because we wanted to know which surface area. You get a bigger surface area in this case is more effective. And what you see is that it depends how many pillars you put in. Very simple physics. If you put too many pillars, the diffusion of the gas inside the pellet structure is not very effective anymore. And then it does not matter that much whether you freeze dry it or you air dry it. But if you have the right content, you see quite a big difference between the air drying and the freeze drying, and you get quite a good loading. It's not perfect yet, but it's the right way to go. So 4.5 is these here are the ideal loadings, but it doesn't make that much of a difference whether it is air dried or freeze dried, because it is the nanometer structure which is the most important. And as long as the flakes are small, the gas can reach it. So that brings me to the end of what I wanted to tell you today. So a bit of physics and a bit of material science. I have all these wonderful PhD students who have worked on this material and whose story I told you today. And then there are my other colleagues, both in Groningen, but also at the synchrotron in Trieste, and of course Jonas Beckert in Antwerp for the theory. And then of course we got money both from the Dutch and from the EU, and I could not have done all the material science part without a very capable materials chemist, and that's Dimitrios Gournis of the University of Ioannina, and many of these PhD students we have supervised together. And I thank you very much for your attention.
Thank you, Petra, for your talk, for your interesting talk. Now we cannot clap, but we do. Now we are open for questions. I don't know if Jorge Alejandro Reyes Esqueda.
Yes, thank you. Maybe my video could be open, please. If not, okay. Hi, Petra. Very nice to see you again. I'm not working anymore in the graduate program of the physics on the UNAM. I'm more dedicated now to my research work, and I was very, very happy to see you. But of course, I'm impressed of all the work you have done with the modification of these 2D structures. And I was wondering about all the things you have mentioned. If you have something to tell us about the optical properties of this pillar, the graphene, or all the 2D pillar in some way, because I can think a lot about possible applications in photonics, especially in biophotonics or nanophotonics. I will be very happy to hear something about the optical properties. Thank you.
Yes, of course, there are also exciting optical properties, but since I'm not specialized in optics, I don't do that myself. But if you want to have any materials from us and you want to try out some things, I'm very happy to provide you with anything you would like to have. Just explain to us what you would like, and we will see if we can make it, characterize it, and then give it to you for the optical properties. Of course, there are very exciting things that one can do, because again, one can use it to get globally a different structure than you can get in any other way. So it's very exciting. Yes.
Great to hear you. Thank you for your answer. I'm going to contact you directly for materials.
Yes,
of course, I'm looking for
perfect.
materials like this. Actually, I'm going to France in 1 week, to Lyon. Maybe from there I could write to you more calm.
Perfect. Yes.
And look at your site, looking for the precise material to start a collaboration on this. Thank you very much. You're working for me very soon. Thank you.
Good.
Okay. Jaime Pestrosvani has a question.
Good afternoon. My question is whether out of this research patents can be obtained and whether you have obtained any.
Patents, I try to avoid to make patents because it's the same kind of work as when you write a publication, but only 2% of all patents ever make money. And you lose a lot of time with it. And most people don't know that of all the universities in the world, there are only 32 who ever made money on patents. So for people at the university, it is, in my opinion, a good idea to collaborate with somebody in industry and then to make privately a deal where you say, okay, you pay me a PhD student and you make all the patents that you want. And I don't want to be bothered with that. But this is my personal opinion.
Thank you.
Okay, thank you. I don't know if we have more questions or in that at the YouTube. No?
I had a question.
Okay. Yes, Gerardo, please.
Well, thank you very much for this wonderful talk. I was wondering when you showed these results about, I think, magnesium diborate, superconductivity, when you were reducing,
Yeah.
you showed that there is some different kinds of Cooper pairings, but I was wondering, you
Yes.
showed that there were some phonons. These were flexural phonons or in plain phonons, because it was not very clear for me.
I'll send you, if you send me an email, I'll send you the paper. So essentially, they are different phonons for the different Cooper pairs that intervene. So it's quite a complicated story, but Jonas did a beautiful calculation on all of it. And what he also showed is that when you put strain on the very thin layers, the superconductivity should actually become more more robust. So there is a way to get the critical temperature up, but you have to strain the lattice, and we have not found yet a good way of doing that, because the magnesium diborite is really difficult to grow in a good fashion. So we're still looking for a solution, but it's very, very interesting as a system to look at.
And can I make another question or?
Sure.
Okay, just a short. When you show these results of graphene doped with nitrogen,
Yes.
I was wondering if there's some kind of mobility edge or all states become somehow localized, because there is a huge debate since a long time ago that it's not possible to have mobility edge when you have a two-dimensional systems. So I was wondering if you have something like a mobility edge or not, because it would be very important.
Well, the point is that you never have a completely two-dimensional system, because graphene itself is only stable because it actually makes a 3D structure when it is freestanding. So it gets all these 3D corrugation. Otherwise, it wouldn't be stable. And other layers, like when you dope it, you always have it on a substrate, or you have it on something else. So I don't think that there have been any studies yet of freestanding dope material, but I would expect that again, it's not 2D. Yes, it is 2D in the sense that you have one plane of atoms, but you have to always consider that even when it's freestanding, it can assume a certain 3D structure, as we have seen in the case of graphene. So all these statements that come from theory, it is 2D and therefore it cannot, they are true, of course, but we cannot make that experimentally. Experimentally, we have something which is actually, which has a 3D structure, or which interacts with the substrate. And the cases where you don't have the interaction, this is why I showed you the graphene on the copper oxide. It's an absolute exception that you get a situation in which the material does not feel the substrate. And it's not the normal situation. Normally you have a lot of interaction with anything you put it on.
Okay, thank you very much. Yeah, thank you.
I don't know if someone else has have a question. Okay. Francisco Sanchez is asking if you have tried to synthesize silicene, silicane, which is the hydrogenated silicene instead of germane.
Yes, the answer is yes, but it's not as nice as the germane. But publications are lined up on that as well. So yes, the answer is yes.
Okay. I don't know. Someone else opened the video. Okay. Yes, sure.
Hi, Petra.
Hello.
Well, it was a really good presentation. I love it. And so my question is related to, I was thinking, so in your presentation, you mentioned some researchers or collaborators in this research. And I consider that these collaborations are always important. And so my question is about what was or what is your role in this study, and what surprised you the most in this research?
So essentially, I love collaborating with other people, especially if they think in a very different way from me, because then I know that I can help them in characterizing their material with my characterization techniques. But at the same time, when we talk, we come from two different directions, and then surprising things happen because you don't think about the same object in the same fashion. A physicist thinks about something like germane completely differently than a chemist thinks about it, and so it is when you collaborate and when you have ideas that you say, oh, but we could try this and we could try that, and you look for other colleagues who are then specialized in looking at particular aspects, that exciting things happen. So I have been fighting my whole life with people who said, but you do so many different things. You will never get famous because you have to specialize on one thing. Well, I think my life is too boring if I specialize just on one thing. So what I specialize in is my techniques and my surface science knowledge and my characterization techniques. And then I can collaborate with many people and help them and look at things that I find fascinating and try things out. So I think that this super specialization, that might be good for some people, but for other people it doesn't work. So you should be in the place where people appreciate the way you like to do science, and then you're productive and you have fun.
Oh, wow. Okay, that was a good answer. I really appreciate it. Have a good day. Thank you.
Thank you.
Okay, I don't know if someone else has questions. Yes, Pablo Calderon. Okay, let me just read the chat. He asked how susceptible to corrosion from the biological environment are these structures, the pillars, and how much can you control the mechanical properties while you build them? How good is the cellular addition to them? These are three questions, no?
Yeah.
Okay.
As usual, there is no general answer. Every system behaves differently, but as I said, we tried them in different. We tried out graphene oxide with a lot of environments, germanane with less environments, and germanane degrades a bit faster than graphene oxide, that's for sure. Graphene oxide, you can also recycle it. So many of these, if you don't need the organic pillar, but you only need, for example, the silicon oxide cage, which keeps it apart. Once you have put it in, you can actually heat it up, get rid of the organic part and use the pellet structure, and you can recycle it many times. So for the CO2 we tried out, and we tried now also we are making a material for hydrogen storage, and there also we tried out to recycle it many times, and there is absolutely no problem. So it depends on how much you heat, how stable it is. So every time you need the organic part, of course you can't heat too much because it will break apart. But for the rest, the materials are very stable. So if you don't change the conditions in a way that the pillar has an easier time to get out, as it was in the case of the adamantilamine, when you put it in an acid environment, then it starts to leach out. But that's what you want in that case, because you want to kill the cancer cells. So you want this to happen only where you are in an acid environment and nowhere else. So one has a lot of ways to tune what you want to happen and how it happens, and you choose your pillars according to the application and what you want to do.
Okay, I don't know if someone else has a question. If not, I have a question. When you talk about the ibuprofen, ibuprofen is a chiral molecule, and one of the I don't remember which enantiomer, it's not good for liver, for example, for the liver. And the other one is the one that has this effect, no, that anti-inflammatory and so on. And in this case, for example, when you have these pillars, is it possible, how you can control, for example, that it delivers it more in the intestine, not in the gastric, and how you can reproduce, or how you can control this from the structure of the pillars, or if you can choose, for example, one enantiomer over the other, and so on. I don't know if you have tried these kind of things.
We have never tried to do enantiomer separation with the pellet structure. That we have never tried, but the way it interacts is again whether the pillar is happy where it binds, or whether the molecule is happy in the environment where it is, or whether it prefers to bind to the solvent which is outside. So when you put these tiny flakes, so when you do this pillaring, the material exfoliates very well. So you have very tiny flakes afterwards, which are maybe 5 layers or 6 layers or things like that. So you have very tiny flakes. So it's very easily accessible by everything which is around. And depending on whether the molecules you have in the flake are more strongly bound inside, or whether they prefer to bind to the solvent, they leach out and they bind to the solvent. So that's how you use it. So you choose your pillar, and actually we work a lot with theoreticians. So when we have an idea of what we want to make as a structure, we first ask somebody to check it out in silicio, and only if our idea is correct, and then we make the effort to actually make it and to try it out. So very often we have several ideas about which pillars you could use, and then our colleagues help us to decide which one is the best one. So actually, George Foudakis does a lot of work on this for us. So, and often he publishes alone, because it's quite interesting just to look at it from a theoretical point of view. So, yes.
Okay, thank you. I don't know if someone else wants to make a question. If not, well, thank you very much for your talk, Petra, for your time. For sure,
It was very fun. Thank you.
It's dinner for you. And next time, we hope you can visit us here.
Yes.
Okay.
As soon as we can travel again, I'll come again. So don't worry.
Okay. 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 Well,
Thank you. Bye bye.
Thank you. Gracias a todos. Que estén muy bien. Hasta luego. Bye bye, Petra.
Bye bye.